Okay, for section 14.2, we're going to talk about colligative properties and colligative properties of solutions when you have a solute being dissolved in a solvent. So first off, what are colligative properties? Well, colligative properties are those that depend on the number of particles that are dissolved in the solution. You most commonly know it as the concentration of the solution. A colligative property is not dependent on the actual solute, what is being dissolved. It's just how much of that solute is being dissolved into the solvent, making the solution. So the three main colligative properties we're going to talk about are vapor pressure depression, freezing point depression, and boiling point elevation. So you really need to understand what depression and elevation mean. So if something is depressed, it is lowered, depression, and if something is elevated, it is becomes higher or raises up, elevation. In the actual calculations we will eventually do, you need to use concentration in the form of molality. And we haven't really studied molality because we've gone out of order. We only studied molarity. So just so you're aware, molality, let me get a different color here. Molality is when you have moles of a substance, what's being dissolved over kilograms of the solvent doing the dissolving. So moles over kilograms gives you molarity. And molarity is abbreviated lowercase m. So you really need to watch that because we just talked about molality, we just talked about molarity, capital M. We're going to molality now, lowercase m, where molality, the concentration, is equal to moles of solute dissolved in kilograms of solvent. So the first one I want to talk about, colligative properties, vapor pressure depression. So you have to understand that a boiling point and a freezing point of a solution is going to be different from the pure solvent. So a pure solvent would be like water, and a solution would be like sugar or salt water, something dissolved in that water. So the boiling and freezing point of pure water is different than the boiling and freezing point of sugar or salt water because there is something dissolved in the water. You also need to know that vapor pressure is basically the pressure caused by molecules escaping as they vaporize. So they go from the liquid phase to the gaseous phase. The pressure that happens when that change of state or change of phase occurs. You can also say that vapor pressure is a measurement of what tendency do molecules have to actually escape from the liquid form and go to the gaseous form. So the actual definition of our colligative property, vapor pressure depression, basically says the vapor pressure of a solution, which as I said is a solvent and a solute combined, is lower than the vapor pressure of the pure solvent. And it makes sense because it's vapor pressure depression. Depression means to go down to lower, and that's exactly what the definition says. So if you look at the picture, on the left we have pure water, and you can see there are many arrows going from the liquid to the gaseous phase. And there are some that are coming back down, condensing, but we're worried about the up arrows. So a lot of particles are escaping the liquid phase and moving to the gaseous phase. When we look at the right picture, we've got water, but now we have something dissolved in the water, the red. We'll say salt. Now, if you look at the arrows, there are very few arrows which are showing the escaping of the liquid phase to the gaseous phase. So the vapor pressure has been depressed. It's been lowered when you add that solute to the solvent. This also means that the solution will remain a liquid over a larger temperature range because it isn't as keen to move to the gaseous phase, so the full change of state from liquid to gas will not take place at the normal temperature it would. So if water evaporates at, if water evaporates at its normal temperature And the normal boiling point of water is going to be 100 degrees Celsius or 212 Fahrenheit. We're saying that if you put salt water in it, it will lower the boiling point and it will remain liquid for longer. And that's why it takes longer for it to boil. Oops, I just said the wrong thing. I'm so sorry. It's going to lower the freezing point, so it freezes quicker at a lower temperature and it raises the boiling point. So vapor pressure depression is when you are reducing the vapor pressure because you've added a pure solvent now with a solute. So if you think about in the winter, they put salt on the roads and the whole point is to melt the ice. So think about this, it lowers the freezing point. So if you put ice, if you have ice and you put salt on it, the salt kind of helps to activate the melting process. And then with that salt there, it will take the water at a lower temperature to freeze, which is good because hopefully it won't get a lower temperature and the salt will take care of it. It will liquefy the ice and then it'll evaporate and then will be no more ice on the road. Okay, so getting to the next colligative property, freezing point depression. And this is abbreviated delta TF. Delta meaning change of, T for temperature, because it's a freezing point, a freezing temperature, and F for freezing. So freezing point depression basically says a solution freezes at a lower temperature than the pure solvent. And the difference between the freezing point of the pure solvent and the new solution is the freezing point depression. So we know the freezing point of solvents, water for example, 0 degrees Celsius, 32 degrees Fahrenheit. If we add something to it, it's going to depress the freezing point and make it even lower. Freezing point depression. So this is the equation you need to know. Delta TF, freezing point depression, is equal to KF, which is a constant, depending on the solvent you have, times lowercase m. So in this case, for units, delta TF is going to be in degrees Celsius because we're determining the freezing point depression. How much lower is the freezing point? KF is a constant, as I said, it's the molar freezing point constant that is dependent on the actual solvent. So you have to see what is doing the dissolving, what's the liquid. That unit is degrees Celsius over lowercase m molality. And then m, lowercase m, is molality, and that is moles over kilograms. So we'll do some practice problems. So this chart is helpful. It tells you what solvent and then the KF value, which is a constant. So if you're having a water-based solution, which is common, you would use this value for delta or for KF. If you had acetic acid, you would use this one. So you have to look at the actual solvent given to you in the problem. And these are all negative. So you're going to end up with a negative answer for delta TF because of that. I also gave you the normal freezing points. So you need to do this because if I ask you, what's the new freezing point, you would take this and subtract the freezing point depression to determine how much was the freezing point depressed. What's the new lower freezing temperature? So we'll do this in some problems. Okay, so first one. 17.1 grams of our solute, which in this case is C12H22O11, that's table sugar, is dissolved in 200 grams of water. So I have my amount of water, and I also know that my solvent, my liquid, is water. Find delta TF, so that's step one. Find the freezing point depression, and also find the new freezing point, the temperature at which the solution will freeze compared to pure water. So what temperature will the sugar water freeze at compared to just pure water? So the first step is to convert grams to moles of the solute, which is the sugar. So this is just a unit conversion. So I'm going to take 17.1 grams of sugar. I'm going to moles. So 1 mole is going to be on the top. What will go on the bottom? It's going to be the molar mass of this compound. So up here I have 12 carbons, and carbon, I'm rounding, is about 12 grams each atom. I have 22 hydrogens, that's about 1 gram each. And then I have 11 oxygens at about 16 each. You do not have to round, but if you do, you're going to get the exact same answer as me. If you don't round, you'll get something a little bit different, which is okay. All right, so 12 atoms of carbon at 12 each gives us 144. 22 grams of hydrogen at 1 gram each gives, or I'm sorry, 22 molecules of hydrogen at 1 each gives us 22. And then 11 oxygens at 16 each gives us 176. So if I add those all together, I get an atomic mass of 342. So that's going to go down here. My molar mass is 342 grams per moles. But I don't need grams per moles because the mole's up here. So I just actually have to write grams at the bottom. That way my units cancel. And I apologize for that. If I said atomic mass, I meant molar mass. So 342 or something close to that. If you round it a little bit different, that's fine. Now I can check my grams is going to cancel my grams. I'm left with moles. That's what I want. So doing the math, 17.1 times 1 divided by 342 gives me 0.05 moles of sugar. Okay, second step. I need to convert grams to kilograms of solvent. That's my liquid. So this is water in this case. So I have 200 grams of water. I need to convert it to kilograms. So you need to know that 1 kilogram is equal to 1,000 grams. So I have 200 grams of water. I'm converting it to kilograms. So 1's going to go on the top, just for my conversion. The 1,000 goes on the bottom, just for my conversion factor. So doing that, I get that I have 0.2 kilograms of water. And I don't necessarily care if you show all this work, but I do need to see the numbers you're using, and especially the molar mass, so I know if there's something wrong where you went wrong. Okay, so step 3. I said that molality is equal to moles over kilograms, specifically moles of solute over kilograms of solvent. So here's my mole number. Here's my kilogram number. I've got moles per kilogram for units. They're not going to cancel. That's okay. That's what I want. And I get 0.05 divided by 0.2 is 0.25. And I could write moles over kilograms, but I can also just write M. They mean the same thing. Okay, so now I finally have everything I need to actually solve the problem. So I'm using the equation delta TF is equal to KF times lowercase m. So I need to look at the KF for water. So I'm going to go back on my chart. Here's water. I need to use this value for KF. So negative 1.86 units degrees Celsius over M times M, which is up here. Now the M's are going to cancel. I'm going to be left with degrees Celsius, and that's what I want. So doing this math, I find that delta TF is equal to negative 0.465 degrees Celsius, or you could round that to 0.47. So that takes care of this. But it still asks me, what will the new freezing point be? So going back once again, I'm looking at water. The normal freezing point is 0 degrees Celsius. So I'm just going to write that as a note so I know. I'm going to put normal is 0 degrees Celsius. I want to figure out how much was this freezing point depressed. So I have to subtract the depression, and I know it's a negative, but I'm not going to subtract a negative because then it'll give a positive. So your number should always go down. This is right to say this is negative, but you don't want to do minus a negative because that makes it a positive. I know mathematically that's confusing because the negative is there, but you're just subtracting. So the normal freezing point of 0 minus the depression gives me that my new freezing point of this solution of sugar water is negative 0.465 degrees Celsius. Now I know what you're thinking, they're the exact same numbers. Well, they are because I'm subtracting this number from 0, the normal freezing point of water. So when you have water, these will still be the same, but you need to still say which is which. If you're not using water, they're not going to be the same number. So just be aware of that. So make sure you answer both parts of the question. All right, let's try another one. So we have 269 grams of C6H5OH. It's dissolved in 200 grams of water. Once again, find delta TF, freezing point depression, and find the temperature at which the solution will freeze. So once again, first step is to go from grams to moles of solvent. Of solute. So I'm going to take 2.69 grams of C6H5OH. 1 mole goes on the top. And what's my molar mass? Well, I have 6 carbons at about 12 each. I've got 6 hydrogens, 1 each, and I've got 1 oxygen at 16 each. So doing all of that math, I get that my molar mass is about 94. So 94 grams, C6H5OH, cancel out, grams on top. If I do that math, I'm left with moles, and I get 0.029 moles. You can put 0.03 if you want. Okay, step 2 is to go from grams to kilograms of solvent, which is water. So I have 200 grams water, 1 kilogram equals 1,000 grams. Doing that math. Okay, 0.2 kilograms of water. Now I can do M equals moles of solute over kilograms of solvent. And I get a number of 0.145 M for molality. Or if you put 0.15, that's fine. Now, after all of those steps, I can finally use this equation. So KF is still negative 1.86 because I'm still using water. That comes from my chart. And I'm multiplying it by my molality. Lowercase m's will cancel out, and I'll be left with the degrees in Celsius. So doing this math, I get negative 0.26. You should always have a negative answer for freezing point depression, delta TF. Because this number, the KF is always going to be negative. Okay, so that's my delta TF, that's taken care of. Now, what's the freezing point? So I'm talking about water, right? So the normal freezing point from the chart I showed you is 0 degrees Celsius. To find the new freezing point, I have to take my original and subtract delta TF. So my new freezing point is negative 0.26 degrees Celsius. Once again, these are the same numbers, and that's because we're using water. When you don't use water, this is not going to be 0, so you're not going to have the same number. Okay, so that's just using the delta TF equation, kind of 4 steps. What if I ask you to rearrange the equation and solve for M molality? So given this equation, algebraically you would first have to divide both sides by KF, and that's it. So delta TF divided by KF equals lowercase m. And as far as units go, I've got degrees Celsius on the top, degrees Celsius over m on the bottom. So those cancel, and I'm left with M molality. So try an example of this. Okay, a water solution, so that's important to know, contains an unknown quantity of solute and is found to have a freezing point of this. So freezing point, not freezing point depression, freezing point. What is the molal concentration? So we're finding lowercase m. So delta TF over KF equals m. So I need to know what's my normal freezing point of water, and it's telling me this quantity of solute. So solution with solute has a freezing point of negative 0.23. So my normal freezing point of water from that chart, you don't have to find it, look it up, it's in the chart, is 0 degrees Celsius. I'm going to subtract my new freezing point, and I get a difference of 0.23 degrees Celsius. So that's delta TF. Has to be a negative number. And then KF for water, that comes from your chart. So simply dividing these two is going to give you about 0.123. My Celsius is cancel out, and I'm left with M. This is the molal concentration. Okay, try another one. The freezing point of an aqueous solution of glucose, so aqueous means water. The freezing point of this solution is found to be negative 0.325 degrees Celsius. What's the molal concentration? So once again, using this equation, find lowercase m. I'm talking about water. A normal freezing point from your chart is 0 degrees Celsius, and the new freezing point of solution is negative 0.325. Gives me negative 0.325, and that is delta TF. So you have to use the new freezing point and the old freezing point to find delta TF if it doesn't say freezing point depression. If it just says freezing point, you have to do this work. So I've got negative 0.325 degrees Celsius over my KF, once again water, because I'm an aqueous solution, negative 1.86 degrees Celsius over M. And doing that math, I get a concentration of 0.174 M. You can always plug it back into the original equation. So if you look at the original equation, if you plug the numbers back in, it should be very close to the delta TF. So let's see. Negative 1.86 times 0.174. I got the delta TF is equal to negative 0.324. Pretty close to my actual delta TF that I calculated. Okay. Hardest part. What happens if I ask you to find the equation for molar mass? Well, molar mass isn't even in this equation right now. So you have to derive it. So I don't necessarily need you to memorize this, but I do want you to follow along. So this is our starting equation. But what did I tell you that molality is equal to? Well, I told you it equals moles of solute over kilograms of solvent, and kilograms is mass of solvent. So I'm going to take out the kilograms. Instead of just saying the actual specific unit, kilograms, I'm just going to say mass of solvent. Okay, so I'm going to rewrite this. I'm going to start up here so I have enough room. Delta TF is equal to KF times moles of solute over kilogram mass of solvent. All right, so that's a start. But if you think about moles, what does moles equal to? Going way back to Chem 1, moles is actually going to be equal to the mass of solute over its molar mass. Okay, that's how we get to moles. So I'm going to write this again. Delta TF is equal to KF times, now I'm going to sub in this for moles. So times moles, oops, I'm going to sub it in for moles, so I don't want to write moles. Mass of solute over the molar mass of the solute, all divided by the mass of solvent. So all I did so far was I took this equation and I put it in for M, and then I took this equation and I put it in for that. So now I've just expanded and derived. Okay, I want to get molar mass by itself. Well, right now, mass of solvent is on the bottom. Okay, so I'm going to multiply by that. Remember, that's in kilograms. So that's going to cancel out. So now I'm left with mass of solvent in kilograms times the TF equals KF times mass of solute over molar mass of solute. So I'm getting closer. Okay, now I want to get molar mass on the top so I can solve for it. So I'm once again going to multiply both sides, and this time by molar mass. I just wrote mass molar. Molar mass. Do that to the other side. So now my equation is molar mass times mass of solvent times TF equals, whoops, F, because this is going to cancel, times mass of solute. Okay, so now I have molar mass on the top, but I want it by itself. So I'm going to divide both sides, mass of solvent, and delta TF. It's a long process, but this is how you derive equations. Okay, so all this is going to cancel out. So my final equation, and if you want to abbreviate molar mass, you can abbreviate it capital M, capital M. I know there's a lot of M's going on. Okay, so my final equation is molar mass, capital M, is equal to KF times mass of solute and that'll be in grams, divided by the mass of solvent in kilograms times delta TF. Oh, that took a while, but here we are. I now need to use this equation. So once you get the equation, it's pretty easy. Two things on the top, two things on the bottom. grams for mass on the top, kilograms for mass on the bottom. KF is degrees Celsius over M, and delta TF is degrees Celsius. Okay. And what's my unit for molar mass? Do you remember? It's going to be grams over moles. I can derive that for you if you want, or you can just trust me. Okay, so let's try this example. 99 grams of unknown solute is dissolved in 669 grams of water. The solution freezes at negative 0.96 degrees Celsius. Find the molar mass. So once again, capital M molar mass is equal to KF times mass of solute in grams divided by mass of solvent times delta TF. Plug and check. All the information we need is here. So KF, well, I have water. So going back to your chart, KF for water is negative 1.86 degrees Celsius over M. Mass of solute right there, 99 grams. Mass of solvent, I need it in kilograms. So I have to divide by 1,000. And the last thing I need is delta TF. So remember, if it gives you the new freezing point, which it says right here, the solution is the new, compared to the pure, is this. My actual normal freezing point of water is this. So I subtract, and my delta TF is negative 0.96, and that should always be a negative number. These negatives are going to cancel out, giving us a positive molar mass, and molar mass has to be positive. Okay. So delta TF and KF are always negative masses, and molar mass has to be a positive number. So I would put a parenthesis, plug the top in, parenthesis, divide, and then a parenthesis, type the bottom in, parenthesis equals. That's how I would do it. So my answer is about 286.72, and I know my unit for molar mass is grams per mole. If you're curious to see how I got it, message me. I'll show you. Okay, so that is the molar mass of this substance. Okay, try another one. So find the molar mass of 22.5 grams of solute dissolved in 250 grams of ether, and this is the solution's freezing point. Okay, so once again, I just like to have the equation on the screen to see it. Okay, so now I'm using ether instead of water. Let's go the whole way back to my chart. It's going to sound weird for a minute. I now have to use these numbers, okay, because I'm using a different solvent now. So I need to use this KF value and this normal freezing point. So let's go back to the problem. Okay, so my KF for ether is negative 7.9. My mass of solute is right here in grams. And then I'm dividing by the mass of solvent. So I have to change this to kilograms. So I divide by 1,000. And then I need to find my delta TF. So once again, that's not the freezing point, that's a freezing point depression. So I know that the original freezing point of ether is, let me go back to my chart, my notes. The normal freezing point is negative, whoops, it's negative 116.3. Okay. I'm told that the solution, the new freezing point, is negative 117.1. So this went down. Okay, I know it looks like it went up in number with negatives. So what's the difference here? The difference is negative 0.8. So I took negative 16 minus a minus, I get negative 0.8. Your delta TF always has to be negative. Okay? So I would plug the top in, divides by, plug the bottom in, equals. So what is the molar mass of this compound? You got something close to 201.38-ish. Has to be a big number, has to be positive. Or I should say normally it's a big number, has to be positive. So that is using the freezing point depression equation in 3 different ways. Solving for delta TF, solving for M, molality, or solving for molar mass. The reason I don't have you solve for KF is because they're constants and they're given to you. You can prove it if you want, working backwards, but I don't have you solve for that. So that is the second main colligative property, freezing point depression, and don't forget we also talked about vapor point depression, vapor pressure depression.